Hello, everybody always waves. Hello, we're here. Okay. You move. There we go. All right, so this is our last of this very short unit where we had reaction rates and electrochemistry. Like, it's a super quick unit. You got a test after this, and then we move into our last instructional unit, which is nuclear and organic chemistry. And then your final project is a separate unit. It's set up that way just because of the way the grade book works. I set it as a separate unit. All right, so today, if I can keep my voice, we are going to talk about one of our favorite science smackdowns in history, which some of you already know well. Some of you don't know so well. You'll know by the end of this. And we're going to finish up our chat on electrochemistry. There is a lot of historical perspective here because I think it's a little more interesting than some of the more dull nitty-gritty business. So when you get into the narrative of how we got to where we are, it's pretty cool, actually. So let's talk about our historical perspective on electrochemistry. Now, this is something that you may not realize it, but pretty much almost every discipline in science, if you whittle it down, it's electricity. Biology whittles down to chemistry, whittles down to electricity. Chemistry whittles down to electricity. Think about it. An atom is held together because you've got negatively charged particles in your cloud on the outside, positively charged particles in your nucleus in the middle. It really is the basis of the entire planet and how it functions, well, the universe, how it functions. So if you find it interesting, you can get very, very deep into stuff involving electricity, electrochemistry, neurology, if you really enjoy it when you get into biology, everything. So our historical perspective is going to start way back, 640 to 646 BC, 546 BC. We had a guy named Thales of Miletus, and he's the first one that's credited with the discovery of rubbing amber with a cloth or fur and then having it attract. When it says light objects, it means objects with little mass. So what do we know this as today? Yeah, this is static electricity. This is like, your sock sticks to your pants when you pull them out of the dryer, right? You ever had socks and stuff stuck to it, they pull apart? Yeah, right. Okay. Now this is what's interesting about it. What's amber?
A stone. Oh, like a gemstone.
It is. What's it? Is it a mineral? What is it, James? It's crystallized tree sap. Yeah, it is. It's a semi-precious stone. It's a gem, like you find it in jewelry. What color is amber?
Orange.
Yeah, it's
It's
amber. Like it's a color called amber, right? It's like a gold color, right? Kind of like this, or like this orange over here. So it's a golden color, usually clear. And because it's tree sap, sometimes you can get ancient life forms that get stuck in it, like bugs. Anybody ever seen the original Jurassic Park?
Yeah.
Yes. Okay. The little mosquitoes in the amber, they go in. Yeah.
That would never work because the DNA would break down completely.
Potentially, but they haven't found DNA that's like that old in amber and stuff yet that they can use that well yet. But sometimes under the right conditions, you can get DNA that hangs on for a very, 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 very long time. So maybe not that long, but that's the idea, right? Okay. So this is why this is interesting, because we've been using this word electron all year long, and you've probably heard it most of your life. It comes from the Greek word for amber. There you go. Okay. So that's where the word comes from, because he was rubbing amber with fabric or fur and then getting things to be attracted and stick to it. So when you hear the word electron, it's amber. It's the Greek word for amber. Fascinating, right? Who knew, right? So this is a bust of this guy. He looks real friendly. Yeah, good old Thales. Thales, lighten up. So we had Thales. Yeah, Thales. So then the next big jump in our understanding of electrochemistry and electricity is Otto von Guericke. I believe it is Guericke. 1602, 1686. invented the first electrostatic generator. So I don't know why he chose a sulfur ball. Seems like a stinky choice, but he chose a sulfur ball and it rotated in a wooden cradle, and the ball itself was rubbed by hand and then charged the sulfur ball. And then he transported the charge in the little ball, like the lollipop. See, like he would build up the charge there, he would transfer it to this thing, and then he would carry his little charged lollipop around and be like, zap, kind of like when you do this. And then walk up to your sibling or your mother and go, yeah, right? Everybody's guilty of that, right? If you haven't done it, please do it once in your life. It's fun. Just shock somebody on purpose. We've all done it on accident, but I've been attacked before by children shocking me with, yeah. So anyway, that's the idea. Same concept, right? All right, so then eventually a glass globe replaced the sulfur sphere, probably less smelly and a good idea. And so now it looks more like it did here in this image. And then eventually that whole situation was replaced with these large glass discs, okay? So this is a static electricity generating machine where you spin it and it builds up the static electricity, and then you can collect it and charge an object or yourself if you walk around the carpet, right? With your socks on and zap people. All right, so then we have this dude come in, and this is interesting because we have three different people who are working simultaneously, and they essentially create the same thing. So we have Ewald Jürgen von Kleist, 1700 to 1748. So he didn't live very long, did he? In 1745, so 3 years before he kicked it, he invented the first Leyden jar, which contained mercury and was placed on a metal surface with a ground connection. Well, why would it be called a Leyden jar? That's nowhere in his name or anything else. Well, it's because these two dudes in 1746, so like a year later, independently, physicist Pieter van Musschenbroek and his lawyer friend, I don't know why they're hanging together, whatever, Andreas Caneas, in Leyden, Netherlands. So the Leyden jar gets its name from the place where these guys were working, although these three people were all kind of working pretty much simultaneously. And that's basically what a Leyden jar looks like. And it can actually hold a charge or store a charge. So they can be joined together to store larger charges. So they figured out how to make one little jar, and then they figured out how to connect all the little jars. Kind of like today, if you connect multiple batteries together, it's the same kind of idea, right? Like I've said before, sometimes if you open up a 9-volt battery, you're going to find stacks of little button batteries inside. Same idea. Okay. So all these people were working at the same time. The town these dudes were in here got the credit. So sorry, Ewald von Jürgen von Kleist, you didn't get much credit there. Oh, well. Then we have Benjamin Franklin. And everybody knows what he did, right? Flew the kite on the wire, and the lightning storm, zap, it comes down. Oh, so cool. Everybody was told that story when they were in like preschool, right? Huh? Well, it didn't, the lightning didn't come all the way to him. He had the wire at the top and then the key, and then like he wasn't like, I think so, yeah. But anyway, so, and we've talked about this before. Franklin is one of those dudes who was good. You leaving? Love you. Bye. Franklin was one of those dudes who knew lots about lots of things. And what do we call those people? Polymaths. That's the word. If you're a person, you know, what'd you say?
Jack of all trades.
Jack of all trades. That's somebody who could do lots of things. But polymaths are people that know a lot about a lot. So Franklin knew a lot about science, and he loved to experiment, but he also knew a lot about government. He knew a lot about religion. He knew a lot about writing, right? So, I mean, he understood a lot of different things at high levels, and they're disparate things. They're not like, it's not like he knew a lot about chemistry and physics, which are related so much. He knew a lot about all kinds of disparate things. One of the things I like best about Franklin, when you think of founding fathers, you think of these old guys with powdered wigs, right? He was one of the old guys. Most of them were not old. They were like, how old was Alexander Hamilton?
Like in his 20s.
He was like 19. Marquis de Lafayette was 17 when he came over here to fight. y'all, some of y'all are slackers because he was like fighting wars and freeing countries at 17. I'm looking at you seniors. What have you done with your lives?
No.
Get on the ball, right? Okay. He was actually, Jefferson was like 30, right? Okay. Franklin was one of the older guys. But here's the thing about Franklin. He liked, I think we like to kind of romanticize these historical figures as like these prim, proper, classy people. Does anybody know what kind of personality Franklin had? Like,
He was a player.
he was a player. Oh, for sure. He had women everywhere.
Oh, yeah.
Everywhere. Oh yeah, he was a major player. Yeah, and yeah, paid for that for some health concerns there in the end. He also was a connoisseur of fart jokes and things of this. Like he really, I mean, like he liked dirty old man jokes. He liked 12-year-old boy humor. He was not somebody who, if you met him, you would be like, oh, what a, reverend kind of guy. No, not reverend, not any of the above. He was shocking to a great many people who thought they were going to meet some classy dude, and he came rolling in like telling fart jokes and basically sleeping with everything that moved. Like he was a guy. I mean, I'm serious. Like he was an interesting person. Yeah, but I like that about him. He's interesting. He's not what you expect. All right, so then we had this dude. No, yeah. So in 1780, we get Galvani. So some of you guys know Galvani well, and some of you guys don't know Galvani as well. And we will be talking about Galvani today. So Galvani's Italian. So this is after Franklin's experiment. Galvani was a physician and a physicist. He was an anatomist, right? Which we had that quick little video about him last week, I think. So he was into dissecting and going through anatomy and whatnot. So it's not weird that he would have like dissected frogs out in his lab. He also had a static electricity machine, and he and his assistants had charged a scalpel on the static electricity machine. He touched it to this frog and its little leg jumped. He touched it specifically to the sciatic nerve of the frog. Your sciatic nerve comes out of your very low spine area, goes down your legs. Okay, so it's not surprising that it would jump. A lot of people get sciatic nerve pain. That's like a really common thing that people like go to a PT or chiropractor or whatever for. All right, so keep this in mind. Dude has frogs, right? Dude likes frogs. Dude likes electricity. So here's one of our greatest smackdowns in science history. Our big one from last year was what?
Tesla versus Edison?
Yeah, Edison versus Tesla is the big one from last year. And this was kind of the smaller of the two from last year. But it's always worth reviewing because it's one of my favorite stories in science. So who doesn't know much about Galvani? No, everybody feels they know him. All the people that were here last year know. Yeah, you don't know as much about him. You don't know. Yeah, I was going to say, those of you who weren't here last year may not know as much. So here's where it gets fun. So first we have our buddy Luigi, right? Luigi, good Italian name. By the way, why are all these guys in white wigs?
Because syphilis.
Yeah. So it started as, oh, we all have syphilis, our hair's falling out, it looks bad, let's put on wigs. And then it became the fashion. But yeah, for real, they all had
Because they're good.
and gonorrhea and everything else because because they did. Yeah, and syphilis will cause major neurological damage. It'll mess you up.
Yeah.
So yeah, oh no, it didn't look real. But neither does think about it. Today it's not uncommon to walk by somebody with like pink or purple hair. That's not real either. Yeah, she's got green hair. How common is that? That's not normal. That's not natural, but it's awesome. I love it.
And it's not.
Yeah.
It does actually glow in UV light.
Does it? I've had both purple and rose gold in mine, so I'm with you on fun hair color. All right, so Galvani was an Italian physician, biologist, and philosopher. If you're going to be brainiac, you might as well tell everybody what you really think about everything, right? Okay, so once, while experimenting with some disembodied frog legs, don't ask. We already explained why he had disembodied frog legs. His assistant charged a metal dissecting tool, in this case a scalpel, with static electricity from one of those Leyden jars, and he touched it to the legs, and they jumped.
They're not.
Just touched it to it, it picked up the charge. Yeah, could have been on purpose. I don't know. But this part was kind of accidental. Like so many great scientific discoveries, it was at least somewhat accidental. They didn't expect the legs to jump, and they did. So now they're like, ooh, what happened, right? So this became his fascination with what he called animal electricity or bioelectricity, which he thought, guys, which he thought was hey, Drew, you left the pantry open, dude. Can you go shut it? Thank you. Sorry. Anyway, he thought this was a completely different kind of electricity from what he called artificial electricity, which was what you create when you turn the static electricity machine or you use a Leyden jar. He thought this was a whole different kind of electricity. It's really not, but he thought it was. So this is kind of a diagram of what we had going. There's your static electricity machine. There's your Leyden jar. Oh, there's your frog legs today. Uh-huh. Mm-hmm. They're blown up, obviously.
Why do you think it's different if he got the charge from the artificial?
Great question, right? You would yeah. It's the conclusion he came to that there must be some fluid that exists in living things that generates electricity, not transports, generates. Okay, so different. So that's the perspective he's coming from. All right. So it led him to place the frog legs outside with wires running to him. That's fun, right? You know, just on his little bistro table in his backyard. So now historically, this has taken place after Franklin. So he probably had read or heard about Franklin with the kite and the wire. So he's like, well, what if I put a wire outside to some frog legs in my yard? Maybe something will happen. So you're laughing because it's ridiculous, right? It's a ridiculous idea. All right. So this would have been a fun neighbor.
Yeah.
Sometimes I think that neighbor's crazy because he never stops working in the yard and fighting deer like he's Elmer Fudd. And sometimes I think these guys are crazy because they completely gutted the house and the yard and rebuilt everything. And then they put bee hives in their backyard a week ago. They were bouncing down there, carrying bee. I said, that's bee hives. She's like, yeah. God, now what? So this would have been a really interesting neighbor to have. So yeah. So now things are getting really weird. So put yourself in, you put on your little imagination hats now. So picture this. This is Luigi Galvani's house. This is his actual house. It still exists. You can go see it today, but without the cars in the street. So probably something more like that. Like no cars and no street. We got to take that away. All right. So no cars, no street. This is his house. Cool house, right? All right. So look like that. And anyway, so imagine you're just strolling past and you notice his lovely home and the nice iron fence he had built around it like that. Oh, lovely little iron fence. Oh yeah. Here. Let me make sure this is still, hang on, it tuned off for a minute. So let me make sure it's not sharing. Well, I'll explain it. All right. So this is what I mean by weird. So no, I'll tell you. Okay. I'm just trying to get this set because I know like Caden's not here, so he's gonna need to watch this. All right, so you see this weirdness, and I've been saying that I'm weird, so I appreciate this guy's weirdness. A baby farmer was someone who provided an option for unwed mothers. They could come have their baby with the baby farmer, or they could have their baby elsewhere, but bring their baby to the baby farmer, and that person would farm the babies out to new homes. But this was all for a fee. Like, you unwed mother, you had to pay this woman to take your child, and then someone else had to pay to get the child. So sort of like an adoption agency, but completely unethical. But Amelia Dyer, maybe, but Amelia Dyer,
That's
she was an infamous baby farmer that lived in the UK, and she was a serial killer. Because it was far easier for her to collect the fees from the moms, and when the baby started crying, she would give them Godfrey's crystal, which is full of opium. And sooner or later, she realized that if you gave them enough, they stopped crying forever. So that's the level of serial killer we're talking about. We're talking dozens and dozens and dozens of babies that were sent to her that just disappeared because she did away with them. But
No.
so my point is, I like weird and strange historical things. This dude is the weirdest. Like, this is real life. You would be strolling past, minding your own business, and this was real life, and these frog legs are like, you know, jumping all over and being strange. Like, can you imagine? Can you even imagine? This would be minding your business. This is what you're seeing. Yes. Oh, making frog legs jump.
Are you fed now? It's like sitting on your bed.
So Galvani saw the frog phenomenon as the work of biological organs, and he believed he discovered animal electricity. He discovered something new. He did not, but that's what he believed. Animal electricity. Addie, there's a spare chair in the back if you want it. You can just have Colin and Xander pass it up to you if you need it. You good? Okay. So an electrically charged body fluid generated by the frog existing in a state of disequilibrium. He thought that he had, in a way, reanimated the frog. All right, so he's thinking he's pretty awesome. He'd actually just discovered that the frog's nervous system transports electrical charges, which is what yours does, right? When in contact with two pieces of charged metal, it completed a circuit. Uh-huh.
Like electric eels, are they kind of like what you think of? Is that different?
I don't think he had a clue those even existed, or
It's like the same thing.
kind of, they have an ability to like release a charge that they've stored up, but it's not like it's different than what he was thinking of. He was thinking that organisms must have some charged fluid that flowed around, and that's how their muscles work. He didn't understand the nervous system at all, that the nervous system was transporting the charges. But this is where he was coming from. All right, so then he knew that metals transported this mysterious electricity, but he came to this conclusion that to him was obvious, that there's animal electricity. It was generated in the tissue of the frog and flowing through the metal skewer, hence activated the frog's muscles. And he had this differentiation between what he called artificial electricity, which came from friction or static electricity, and natural electricity. And natural electricity could be anything from like the bioelectricity to lightning, right? It's just in nature. If you're generating it, it's some kind of artificial electricity. Really, it's electricity. But he didn't know, right? So this is where he's coming up with. So he thought that animal electricity was secreted by the brain and proposed that this is what flowed through the nerves. Like, they had a rough idea there were nerves, they just didn't understand how it worked, and that it activated muscles.
Did he mistake an actual fluid for that, or did he just like make one up and never?
He just made it up. There isn't a fluid. Like, I mean, there's fluid, there's electrolytes within your body, but it's not like blood that flows or lymph that flows through your body. That's kind of what he was envisioning, but that's not how it works. But, you know, he's trying. He's doing his best. So then, this was this landmark discovery, and it changed how people understood the nervous system. Like, we knew there was a nervous system. He was an anatomist. He just didn't really understand how it worked, right? But this changed what people were thinking, that electricity is involved. Now we have his nephew, Giovanni Aldini. Giovanni Aldini was a showman, and he was Luigi Galvani's biggest fan. Loved his uncle, thought his uncle was like the be all end all, and started touring Europe, showing people the tricks that his uncle had invented or discovered, right?
Uncle is Beyonce. Now watch me
There you go.
animate this.
Yes. So he went around Europe reanimating the corpses of animals. Yeah, and humans. He did that too. This is where it gets juicy. Okay. I love weird historical stuff, and this is so weird. So this is a famous picture of Aldini, and you can see he has a bowl, and its head's on one table, and its body's on another. Now, remember, we don't have TV. You gotta have money to go to the theater, and even that is not like constant every day. You don't just have access. Entertainment was weird because it was really anything you could go. Kind of like, think of it this way: if you saw a car crash on Instagram, you'd probably watch the whole thing, or a police chase, you'd probably watch the whole thing because it's fascinating, right? But then it was just, if it happened in front of you, you watch the whole thing because that was the only source of entertainment. So for entertainment, Aldini tours around Europe, galvanizing. Okay, this is where the term galvanizing comes from galvani. Galvanizing, galvanized or galvanizing has two meanings. You can be like a galvanized metal, which is a type of metal that's like a plated metal, right? It's galvanized, it's had electricity run through it. You probably recognize it. It looks kind of like hammered. Actually, if you've seen anything that those Magnolia people do, it's probably got galvanized steel in it, right? It's that kind of patchy looking silvery metal. All right, also, galvanized means like to spur someone to action. So like, you hear about atrocities going on in the town next to you and you're galvanized to go fight for justice. So that's kind of what it means. So he starts galvanizing corpses. So rather than using a Leyden jar though, he needed something that could store more electricity. So he traveled around with a voltaic pile, which is a type of battery. All right, so he's hauling this big bag, they're big too. So it's a Leyden jar in this picture, but he eventually got to a voltaic pile. So the most famous demonstration happened in London, January 18th, 1803. And I have researched this incident as well as I can, and I found some interesting things about it. Like I saw like a lot of the police interviews and stuff have been printed out. Police are involved because of this man. 26-year-old George Foster was accused of murdering his wife and daughter by drowning and was hanged in London. So I looked this up. They were not living together at the time. He was like working in a factory. He'd been in they had both ended up in the same pub. He and his wife, his daughter was young, I think less than 2. But anyway, the mother and the baby were found floating in the Thames River. And because they had been seen together at that pub, of course, he's the first. Even today, if y'all don't know this, but if someone goes missing, their domestic or is murdered, their domestic partner, whoever that may be, is your number one suspect always until otherwise ruled out, because statistically speaking, that's who it is, right? Especially if your missing person is female, then chances are it's the husband or the boyfriend. Like statistics, no offense, dudes, but statistically. So if you're going to put your resources somewhere, that's where you go. So of course they look at him and they're like, he must have done it. So he was tried, and you know how great those trials were back there in the 1800s. These were great trials with lots of very strong evidence.
Definitely no.
Right. Hey, so sorry. So dude was hanged in London. Now, hanging people, here's another thing. Yeah, they do that too. When you hang someone, what is supposed to kill them? How are they supposed to die?
Neck snaps.
The neck snaps, yes.
Like the head, like dislocated.
Yes. Okay, if you're a quote unquote good hangman, if there is such a thing, if you're good at your job, the goal is internal decapitation, right? Popping the head off the rest of the spinal cord. The goal is not to strangle someone to death. That is a bad hanging. Those are not, you're not supposed to ever see anybody. That's not the way it's supposed to go. And there's math involved that involves how far the drop is, how strong the rope is, how heavy the person is, so that when they fall, they don't fall and then strangle, they fall and then snap, which is why, historically speaking, hangings were not great for women or teenagers, because the math was different than for grown men. So a lot of women and teenagers who were hanged suffered immensely because they strangled rather than snapped, right? Okay, so here's our weird, it's all in this weird history, right? So this dude's been snapped, which means his brain is detached, but his spinal cord is intact, and his muscles have not been like, struggling for oxygen for a long, long, long period of time because he wasn't strangled, right?
What happened if you like made them fall too deep?
Yes, that did happen many times. If someone was too heavy,
How did they get that high?
if they were too heavy and the rope was good and strong, yes, sometimes you were left with two pieces in the end. Yeah, that was not the goal, but not uncommon. It did happen to people. Gross, 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 and more gross, but interesting, right? Okay, so his body was immediately transported to the Royal College of Surgeons right there in London, where before an audience, Aldini starts running electrodes from his voltaic pile and attaching them to Foster's corpse in various places. Okay, so his nervous system is still essentially intact and undamaged except for that severed point, right? This is like when I told you last week that if you do neurobiology in college, you'll probably be required to decapitate and pith frogs for the same purpose of keeping their nervous system intact so that you can work with it. All right, so he attached electrodes to the jaw and to the ear, and he got this weird one-sided grimace. Audience is like, ooh, cool, look at this dead body making faces, because this was entertainment. This is the Instagram of the day, people, right? So then he even made an eyeball open. People were, an eye open, so you could see this dude's eyeball in one eye. Oh, everybody's, this is the coolest thing we've ever seen. Look at this, dead body's opening its eyes and smiling at us. All right. People are loving this, right? This is what you did for entertainment. Weird to us today, totally normal then. And they were called operating theaters, right? Because people watched like a theater and you did your little whatever on the table for everybody to watch. All right, so now Aldini's aim really, aside from showing off to the world, because he was like the P.T. Barnum of the electrical era, I guess. He really wanted to know how you could help somebody who had experienced trauma. Like, could you restart somebody's heart? He understood you could make muscles move. Could you make a heartbeat? Right? Well, no, not in this case, but I mean, even to this day, medical experiments and scientific experiments, you don't do it on, you don't kill a living person to try and bring them back. You take an already dead person and try and work on things. If his heart started beating again, he's still not technically alive because his brain is detached from his body, right? And that's really where your life is, right? Like your heart's beating, but if you're brain dead, you're just a body, right? It's pumping things. What's you is up here, right? So this is the genesis of our AEDs and our defibrillators today, right? Anybody been trained on an AED?
Yeah.
Yeah, you don't even have these ones today, like you don't even have to really know what to do. It has a voice that talks to you and tells you what to do. Right? So today we can restart a heart. Then they were like, how do we do this? How do we restart a heart? So I love this GIF. This is about right. Yep. This guy has no head in this case, but I think Foster's head was obviously still attached, but not connected to everything else. So see, but back in 1803, Aldini didn't really know. He's fiddling around. Like there's no real like scientific method to what he's doing. He's not conducting this very controlled experiment. He's just goofing off and getting all the public credit for it. Like all the social props because he's so cool, right? I don't know why, but So he kept fiddling around with Foster's corpse with an audience, right? And he moved an electrode down to the bottom of his spine. And then he sat up, like straight sat up. I don't think his arms went up like that. This is a comic, a drawing from the newspaper at the time. This is how the newspaper reported it. See the little demons? Okay, so like this is what played into it. And it actually said, had I not been insensible to fear, now should I be most horribly afraid. Hence, horrible shadow, unreal mockery. Hence, and yet it stays. Can it be real? How? See, it goes on and on with all this. And the little demons are saying, there, we've lost him after all. See, they are bringing him to life again. Notice this was a man condemned to death for murder. So who lost him? The demons, because clearly he went to hell in their mind, right? Because he was convicted of murder and executed. So anyway, this happens. So imagine you're in this room you're watching this dead guy grimace and do all kinds of weird stuff, and then he sits up. It's nobody has ever seen anything like this in their lives. It was huge. It was a huge deal. So for those of you who weren't here last year, does the scientist reanimating a human corpse sound like a familiar story to you? Maybe classical literature?
Yes, Mary Shelley.
Frank is yeah. Exactly. Hello. Sounds familiar, right? All right. Now those bodies are like way dead. They came out of graves and stuff, right? So it's not quite the same thing. So the question is now, did Aldini get this idea from Mary Shelley, or did Mary Shelley get the idea from Aldini? Mary Shelley got the idea from Aldini. Yeah. So Frankenstein is based on some historical events, some real historical events. So, and it says right there, 1818. So 15 years later. Very cool. So 15 years later, Mary Shelley writes this book about this mad scientist creating a monster using electricity to bring it back to life. So yeah, made an impact. Now, here's the crazy thing. Galvani was not universally celebrated. He had a professional nemesis. Who's this guy? Anybody remember? Who is it? Yeah, Volta. Yeah. This is Alessandro Volta. All right. Volta. Yeah. So Volta was another Italian scientist, and they're contemporaries, and he believed that Galvani was wrong about how electricity was generated, stored, and transported. He believed that metals were all that was required, and that electricity was electricity, not animal, artificial, or natural. And Volta was the one to come up with the term galvanize, but he did it with an eye roll. So the term that they used to be, we are galvanizing corpses today, ta-da! They owned that word, that Volta was like, oh, he's galvanizing things. So it was like a jab from Volta that then Aldini owned and was like, yeah, this is what we're doing, all right, we're galvanizing, it's a thing, right? So Volta could reproduce Galvani's results, but he figured he was wrong about how and why the experiments worked. And he was right in that regard. So Volta endeavored to create a device. This is back when Galvani was doing this with Leyden jars, right? He was using Leyden jars and putting them together, and he had a little charge. So he endeavored to create a device, a non-living thing that could do what Galvani claimed bodies could do. And he built a stack of alternating copper and zinc discs separated by thick paper-soaked discs that are soaked in brine. The brine was usually either salt water or sulfuric acid. Why would it be one of those two things?
Very conductive.
Yes, because acids in solution are conductive, and because salts in solution are conductive. So he created this deal right here, which was a tall, indelible sandwich stack, and it became the first battery capable of continuous electric current, and he called it the voltaic pile. But do you remember that thing that Galvani's nephew ended up dragging around Europe with him? It wasn't a Leyden jar. It was Alessandro Volta's invention that he invented to show Galvani was wrong and to kind of one-up him. Ended up Galvani's nephew's like, I'll take that, thank you very much, and then used it and toured it around Europe. So yeah, thanks, poor Alessandro. Yeah, it didn't work for him. Didn't work out. Now he's poor dude. So his own invention kind of used against him. So there's you can read lots about this whole conflict between the two of them. It's pretty fascinating. So just a comic where they're arguing back and forth about what is what. And in the end, they were both right about some things and both wrong about some things. And now we understand them better today, but neither understood, this is what they were missing, the function of electrolytes. Neither of them really understood that. Volta included electrolytes in his voltaic pile, but he didn't really understand the function of them. So that's what it came down to. So a legacy of this entire conflict today, the great science smackdown gave us batteries, much better understanding of neuroscience, defibrillators, EKGs, EEGs, volt, the unit of electromotive force, right? Yep, the measure of how much pressure there is in an electrical circuit is volt, and higher voltage, the more electrical current usually. Galvanize, as in to shock or excite someone into action, or verb, galvanize, which is to coat, another verb, which is to coat in iron or steel a protective layer of zinc. So there you go. We got lots from that. Lovely little debate. So here's our guy Volta. I would like to have been 5-year-old Volta I would not like to have been 5-year-old Volta trying to learn to spell my name because he is Count Alessandro Giuseppe Antonio Anastasio Volta. How many of you have more than one middle name? I just have the one, and it's very easy to spell. This is wild. Count Alessandro Giuseppe Antonio Anastasio Volta. Woo! Developed your first electric cell, which was your voltaic pile, in 1800. And by 1803, Aldini was using it to set up dead bodies. Fun. So it looked kind of like this. Your layers of two dissimilar metals. He found copper and zinc were the best metals for this job, separated by pieces of cardboard or thick paper, soaked in sodium chloride solution or sulfuric acid because they are both very conductive. So he determined that the best combination was silver and zinc, like I just said. And this is a graphic of what the pile would have looked like before he made it transportable. It's like your little mobile unit, mobile battery unit. This is an actual voltaic pile made by Volta in 1800 that is available for you to go view in the Smithsonian today. Looks like that. I mean, it would still work, sure, but that's what it looked like. So glass tube, right? It's got, you can see all the discs in there. So that's what it would have looked like. Pretty cool that they're still around, but you can go see them. So after Volta, the next step in our historical timeline here is 1800. We had an English chemist named William Nicholson and a surgeon named Anthony Carlisle. And they separated water into hydrogen and oxygen, just like you did today. So the experiment you did today has been done since 1800. People have been doing it for quite some time. Pretty cool. So they were the first ones to do that. And then we had Johann Wilhelm Ritter, who repeated their experiment of separating water into hydrogen and oxygen by electrolysis, and soon thereafter discovered the process of electroplating. And he observed that the amount of metal deposited and the amount of oxygen produced during an electrolytic process depends on the distance between the electrodes. Now, electroplating is when you take like a piece of, it's used in industrial purposes, and it's also applications, and then it's also used for like jewelry. You might have silver plated or gold plated jewelry where the metal underneath is a less expensive, sturdier metal. And then you have this very thin layer of precious metal on the outside. So then we had Humphrey Davy. Humphrey Davy's actually a very well-known historical figure. He's kind of cool. So he utilized Alessandro's voltaic pile, right, to isolate elemental potassium by electrolysis. And then he did sodium, barium, calcium, strontium, and magnesium. So he was taking those chemicals out of compounds using electrolysis, like you did today, where you took hydrogen and oxygen out of compound. Good question.
What makes gold and silver so valuable?
So that's actually interesting. It has to do with rarity and scarcity primarily. Also, the characteristics of those two metals, like take gold, for example. Gold's inert. It's not going to interact with anything on your body. It doesn't interact with other things. It's very stable. And it's much more rare than a lot of the other metals. There's some really good videos on YouTube, like why is gold valuable? Like, why do we use gold? Or why should we use gold as a standard? We gave that up years ago. Don't ask me my opinion on that. But why should gold be a standard for economies and things like that? There's tons of historical reasons for it, but it basically has to do with the fact that it's stable, it doesn't interact, and it's rare. So it makes it, and it's pretty. People like it too because it's shiny, right? So Humphrey Davy used electrolysis, and he separated different elements out of compounds, and that was new. That was a cool thing. I feel like, oh, totally new, fascinating. Now we get to this dude, Faraday. If you want to look up a cool scientist that did a lot with electricity, aside from Edison and Tesla, Faraday's your guy. This is a cool, cool guy. So he was Humphrey Davy's assistant before he came into his own right as one of the best known scientists in all of history. So Faraday developed our two laws of electrochemistry, which state that the amount of a substance deposited on an electrode of an electrolytic cell is directly proportional to the amount of electricity passing through the cell, and quantities of different elements deposited by given amounts of electricity are in ratio to their chemical equivalent weights. And if you're still using British pounds, I know sometimes euros and stuff are in use over here, but he's on British money. Just like we have Franklin and Washington and Jefferson and Lincoln and stuff on our money, Faraday's on British money. That's how well respected he is historically. Why would people do
Yeah.
that?
Yes.
But I want Tony Stark too, because he's got the whole innovative thing. No, you don't like him?
The missile thing.
Not sure. I don't know. I don't know. I appreciate scientists. So,
I think us to make all those, we put your dogs on them.
No, what if you're like cats?
We need,
What if you like cats?
we need, we need,
We need banner.
What do we need?
we need the doctor that created the Captain America serum.
Ah, there you go. There you go. So anyway, Faraday's on the 20-pound note. So Faraday is very well known, still to this day. So Faraday also defined a number of terms. So here's the first term. This is the surface at which the negative current, according to our present expression, enters. These are his words. It is the negative extremity of the decomposing body, and it is where oxygen, chlorine, acids are evolved and is against or opposite the positive electrode. So what do you think this would be? What is against the positive electrode? What's the opposite of the positive electrode? Yeah, what's it called? Anode. Okay, so we get anode from Faraday. All right, so now we're getting somewhere. He also said that this is the surface at which current leaves the decomposing body. The positive extremity, combustible bodies, metals, alkalis, bases are evolved here. It's in contact with the negative electrode, and it would be the what, PJ? It's your cathode. Okay, so he's given us the terms anode, cathode. All right, now, many bodies are decomposed directly by electric current, their elements being set free. So what does he call the elements that are now set free in solution? These are your electrolytes, right? Okay, there's another word Faraday gave us. Now, he also said, this is his words, finally, I require a term to express those bodies which can pass to the electrodes, or as they are usually called, holes. Substances are frequently spoken of as being electronegative or electropositive, according as they go under the supposed influence of a direction of attraction to positive or negative pole. I propose to distinguish such bodies by calling those what, which go to the anode. What goes to the anode? Okay. Anions, cations, are we sure? Anions go to the anode. Very good. And then what goes to the cathode? Xander. Oh, cations. Okay. So now we have anions and cations. So then we get together, you call them what? Anions and cations are both, what are they? They're electrolyte, but what are they? Electrons? What do we think? Electrolytes? Oh, they're ions, right? Anions and cations are ions. So all these words, Faraday. Thank you, Faraday, for giving us good words. We like having good words. So the chlorine of lead is an electrolyte. When electrolyzed, evolves the two ions, chlorine and lead, the former being an anion, the latter being a cation. This is his example. Chloride, sorry, yeah, I read it wrong. Yeah, chloride of lead. Yeah. Evolves the two, chlorine and lead. So the chloride of lead. So lead chloride is what he's talking about. Breaks down into chlorine and lead. So that's Faraday. All right, next we get Daniel. So this is John Frederick Daniel, and he's professor of chemistry at King's College London. You have King's College London, you have King's College Cambridge, which is one of the best choirs in the world, by the way. Very cool. And then we had King's College in the US, in New Jersey, which is no longer called King's College. Does anybody know what King's College in the US is now? Princeton. Yes, King's College is Princeton. Yep. All right, so that's why when you hear, if you ever listen to Hamilton, you hear them talk about King's College, Princeton. All right, so Daniel's research developed into the development of constant current cells took place at the same time that commercial telegraph systems began to appear. So his copper battery became the standard for British and American telegraph systems. This is before you had, like our telegraphs are wired to the house, but not all telegraphs didn't begin that way, right? So you had batteries involved, and it was his battery that was the first one doing that. So in 1839, he experimented with fusion of metals with a 70-cell battery. That's a lot of cells, right? And he produced an electric, this is crazy. He produced an electric arc so rich in UV that it gave him a sunburn and damaged his eyesight, likely permanently, and the eyesight of multiple spectators. This is why when you weld, you wear a welding helmet with a special screen, because that light is extremely bright. It will burn your retinas. And yeah, this is lab tragedy situation, right? Like, dude gave himself a sunburn for producing an electric arc. So you've seen electric arcs if you've ever seen like a wire down on the road and it's like shooting everywhere, right? That's basically what he produced. A big one. Yeah. So then ultimately he showed that the ion of the metal rather than the oxide carries the electric charge when the metal salt solution is electrolyzed. So these are some of like the parts of his batteries, these are his patents. This is how they looked, right? So then after Daniel, we got Nernst. So this is this whole big historical perspective, because it's interesting to understand how we got to where we are today, where you've got a phone in your pocket that'll stay on for 24 hours and then uses the internet and everything's connected electrically, right? Everything. So this guy, he used Arrhenius theory. So if you remember, Arrhenius theory is that when you put an acid into solution, you get, or you put a salt in solution or whatever. And anyway, you get up getting your H plus and your OH negative, right? Is in solution. You have an OH, if it has an H plus, it's an acid. If it's an OH negative, it's a base, right? Everybody remembers the Arrhenius theories just on your test, right? So he was using this theory about the dissociation of ions in solution. And he elucidated or came up with or verbalized the theory of galvanic cells by assuming the electrolytic pressure of dissolution, which forces ions from electrodes into solution and which was opposed to the osmotic pressure of dissolved ions. Woohoo, lots of stuff. Now in 1889, he showed that the characteristics of current produced could be used to calculate the free energy. Here's Gibbs again, right? Now we're back to Gibbs. Free energy in chemical reaction producing the current. And now we still call it the Nernst equation. And it's still used because it relates to the voltage of a cell and its properties. So we still use his findings today. Now this is independently Thomson. Who's Thomson? Thomson. Oh, remember we had...
Remember the plum pudding?
Yes, the plum pudding chocolate chip cookie dude who's like, this is what atoms look like. Remember him? Remember him? We had the little rat, sorry, holding up the little plum pudding on the plate like this. Remember him? Okay. The little chocolate chip cookies on the tray or whatever. That guy. So independently of Thomson, he explained why compounds ionize easily in water. Somebody's finally explaining this, guys. Shh, shh, shh. Yeah. So why do compounds ionize, and what compounds ionize and why? And then we still call this the Nernst-Thomson rule. It still holds. And that it is difficult for charged ions to attract each other through insulating water molecules, so they just dissociate, right? Why do you get an H plus and an OH negative? Why don't they just go right back together? Because shouldn't they be attracted to one another? It's insulating within the water molecules themselves, so they don't go back together. So we know a lot of terminology to this dude. Who is this dude? Same guy who gave us anions, cations. That's Faraday. Yes, this is our Faraday. So Faraday gave us voltage, and we can think of voltage as the pressure between two half cells, the amount of energy that drives a reaction. And of course, he got the word voltage from whose name?
Okay.
Alessandro Volta, right? Okay. And then he gave us current. Current is the flow of electric charges, which is electrons per second. And it's an extensive property. And high voltage does not necessarily mean high current. You can think of voltage like pressure. So if you think of a hose and water flowing through the hose, the water flowing is the current. The voltage is how much pressure that water is flowing with. How hard is it being forced through the hose? He also gave us the term primary battery. This is a non-rechargeable battery. like your standard AA, AAA, D cells, C cells, your 9-volt that you used in lab today. Now, we also have other terms that come along. Secondary battery. Secondary batteries are rechargeable. Lithium, your cell phone batteries, these are rechargeable batteries, right? And then tertiary batteries are what we know as fuel cells. They're not always considered batteries, but these are all more advances that have come out of these guys that went way back to our first guy that was BC, right? Rubbing fur on amber, and that's where we started. So galvanic cells. So a galvanic cell or a voltaic cell, oh, don't these two love that they are clumped together for history? Galvanic and voltaic cells, same thing. Fun. These two guys didn't even like each other, and they can't get away from each other hundreds of years later. So induces a spontaneous redox reaction to create a flow of electrical charges or electricity. Non-rechargeable batteries are examples of galvanic cells. Did you use a galvanic cell in lab today?
Yes.
Yes, you did. A non-rechargeable 9-volt battery. When it runs out of charge, it is dead, right? Right. Electrons flow from what to what? They flow from what? What's our first thing? They flow from the what? Which is negative since electrons are built up there. Xander. Flow from your, anode, because they build up there to the cathode, right? Because it's positive, so it attracts the electrons. So this is the thing that's tricky to remember when it comes to batteries. We know that anions are negative because they're an angry onion, right? And we know that cations are positive because they're positively adorable. But it's not what they're attracted to, it's where they're flowing from in a battery that matters, okay? So galvanic cell produces an electrical charge from the flow of electrons, and it's a redox reaction. So many examples of galvanic cells are power sources that generate electrical energy from chemical energies. This is chemical potential energy that is converted into electric energy when it starts flowing. So like I said, AAA, A, D, C, these are all galvanic cells. Conventional batteries supply electrical energy from the chemical reactants stored within them, right? And an alternative approach would be to feed the reactants into the cell as they're required so as to permit the cell to operate continuously. In this case, the reactants can be thought of as fuel, and that's where you get fuel cell, which is why it is different from your standard galvanic cell because you have to feed them in. So fuel cells were not employed for practical purposes until space exploration in the 1960s. The principle was first demonstrated in 1839, though, by Sir William Grove. So we go way back. A Welsh lawyer and amateur chemist. Again, a lawyer, amateur chemist. I think I'll mess around and create a fuel cell. Right. I know, it's so strange, right? And at the time, it was already known that water could be decomposed into hydrogen and oxygen. So Grove tried combining the two gases in a simple apparatus that discovered what he called reverse electrolysis. And that's the combination of H2NO into water, causing a potential difference to be generated between the two electrodes. And then it was not until 1959, though, that the first working hydrogen-oxygen fuel cell was developed by Francis Thomas Bacon in England. Bacon's also another very well-respected dude. Modern cells employ an alkaline electrolyte so that the electrode reactions differ from the one shown over here, right, by the addition of OH negative to both sides of the equation. And although hydrogen has the largest energy to mass ratio of any fuel, it cannot be compressed into a liquid at ordinary temperatures. So if it's stored as a gas, the very high pressures require heavy storage containers. So hydrogen fuel cells are really, really densely thick-sided, heavy storage containers, which greatly, I have no idea, greatly reducing its effective energy density. Some solid materials are capable of absorbing large amounts of hydrogen and can reduce the required pressure. Other fuels such as alcohols, hydrocarbon, and even coal slurries have been used. Methanol appears to be especially promising as a fuel. So these are all different options for fuel. You've seen alcohol funny cars, right? You've seen those, right? They burn alcohol, so they burn very fast, very hot, right? So corrosion, you've seen this, right? Everybody has seen this. Ever open up an old toy? Ever cleaned your room Pulled something out of your closet you haven't messed with, ever cleaned your room? You all go, no, no. What are you talking about, Danny? We don't clean our rooms, jeez. I know some of you don't. But you find a toy, a walkie-talkie, something you haven't used in a long time, and you open it up and you see that, and you're like, crap, now it's ruined, because sometimes it does kind of ruin it. So this is galvanic corrosion. And it's an electrochemical process in which one metal corrodes preferentially. So one of your metals is going to be the one that corrodes more frequently than the other when it's in electrical contact with another and in the presence of an electrolyte. The electrolyte in batteries, like you'll hear them, AA, AAA, they're called alkaline batteries. So they don't contain battery acid. What do they contain? A base. Yeah, alkaline, it's a base. So we always say battery acid, but that's actually not what's in them, right? It's a base. So whether there is electric current or not, the electrodes of a cell have different potentials. And the difference between these is the voltage of the cell. So this is the graphic we use most often. I think I popped it up last week too, didn't I? But this is the one we use most often when we're trying to understand volts, ohms, amps. So your amps is your current, it's flowing along, right? Your volts is the pressure on your current, how hard is it being pushed? And then your ohms is the resistance on your current, is something slowing it down as it goes through. Sometimes you see this and they've put a little cowboy hat on ohm. I particularly like that version because he looks like he's lassoing amp. Stupid, but I like it. So, an electrolytic cell is a cell which requires an outside electrical source to initiate the redox reaction. The process of how electric energy drives a non-spontaneous reaction is called what? Caitlin, do you know? Yeah. Yeah. There you go. Yep. So whoop, whoop, whoop. Animations. They're in the wrong. Electrolysis is what we're looking for, which is what she said. Whereas the galvanic cell used a redox reaction to make electrons flow. Electrolytic cells use electron movement, and it's in the source of electricity. And to cause the redox reaction, in an electrolytic cell, electrons are forced to flow in the opposite direction. So what is the kind of battery that requires an outside electrical source to drive the non-spontaneous redox reaction? Do we know? Do you know, Caitlin?
Acid dry cells.
Dry cells? Yeah. So electrolytic cells. So yeah, you're on the right track there. So rechargeable batteries act as electrolytic cells when they're being recharged. When they're in use, my phone in my pocket is acting as a galvanic cell right now. If I plug it in, it becomes an electrolytic cell. When I unplug it, it's galvanic again, right? So here's your Gibbs free energy. Remember that from a couple weeks back? Yep. Must supply electrons to the cathode to drive the reduction. Cathode is negative, this whole thing, right? Same thing that we've already discussed. So the most common form of an electrolytic cell is your rechargeable battery, like in your cell phone, or used for electroplating. So while the battery is being used, it's galvanic, like I just said, but when it's being charged, it is acting as an electrolytic cell, and that's a redox reaction. Electrolysis is a process by which electrons are forced through a chemical cell, which you did today, right? Thus causing a chemical reaction. The positive charge usually attracts electrons. The electrode providing the electrons is called cathode because the reduction takes place of it. We saw that today. So electroplating. This is the process of plating one metal onto another using hydrolysis. The most commonly, or electrolysis actually, most commonly for decorative purposes or to prevent corrosion in metal. So there are also specific types of electroplating, such as copper plating, silver plating, chromium plating. Electroplating allows manufacturers to use inexpensive metals like steel or zinc for the majority of a product and then coat the outside of it with what they need. And you can even coat it with plastic. But this is a video that shows you how electroplating works. And it's actually really cool. It's kind of cool to watch. This is like, you ever watch How It's Made? This is how it's made. I could watch How It's Made all day. Like it's so fun. So here's how electroplating works.
Is a layer of metal coating an object of a different type of metal. The purpose can be decorative, as in silver plating, or practical. With industrial parts, for instance, zinc or cadmium plating prevents the underlying metal from rusting, while nickel or chrome plating protects against wear. You can plate almost any type of metal. Let's follow some steel aerospace parts as they're about to be plated with cadmium to make them corrosion resistant. For the plating metal to bond properly, the steel surface must be free of contaminants such as oil and grease. Workers suspend the parts over a vat of boiling chemical solvents. As the hot vapor comes into contact with the colder metal, it condenses, dripping down into the vat and taking any contaminants along with it. The remaining solvent residues evaporate, leaving the parts squeaky clean and dry. Next, a worker wearing protective clothing sandblasts the parts with aluminum oxide powder, a strong abrasive. This roughens up the surface so that the plating metal will adhere better. The most common plating metals for industrial purposes are zinc, chrome, and nickel. Think motorcycle parts or sink faucets. Decorative items, on the other hand, are more likely to be plated in tin, brass, gold, or silver. Traditional tea sets, for instance, are often made of silver-plated copper or zinc. The plating process is called electroplating because the key
Canadian
to it all
process.
is electricity. They start by tying strands of copper wire to a copper support frame, copper being the best metal for conducting electricity. Then they attach the steel parts they'll be plating. When they hook up this support to an electric current, electricity will run from the support through these wires right to the pieces. They do the electroplating in a tank. After filling it with water, they add a handful of chemicals to help conduct electricity, because water alone won't conduct it sufficiently. Along the sides of the tank, in bags, are metal baskets. They contain bars or balls of the plating metal, in this case cadmium. Workers connect the support frame with the steel parts to the negative terminal of an electric source, the baskets of cadmium to the positive terminal. Then they switch on a steady DC current, no stronger than 6 volts. The electricity dissolves the cadmium, lacing the particles with a positive charge. They travel through the water and attach themselves to the negative charged steel parts, creating a smooth and even layer of cadmium. Thin plating requires just a few minutes in the tank, thick plating several hours. Then workers rinse the parts in water for about a minute to remove the chemical residues. To make the parts even more rust resistant, workers immerse them in a series of compounds. This triggers a chemical reaction in the plating, enhancing its ability to withstand corrosion. This reaction, however, changes the color. A final rinse in hot water, and this cadmium-plated steel aerospace part is finally ready. From start to finish, the process has taken about 90 minutes. To plate with chrome or gold, they have to use a chemical compound containing gold or chromium. That's because electricity can't dissolve solid chromium well enough, and it can't dissolve solid gold at all. The compound dissolves in the bath like salt, but then solidifies once it reaches the object being plated. Metal plating is very durable, but it's subjected to a lot of wear and tear. The object will eventually have to be replated.
So this always reminds me when I see this video of this plating. So they're running electricity through the pool, essentially, right? The container of water. So this goes back all the way to the Galvani situation, all right? So Jason's degree is in electrical engineering. So when he was in college, one of his professors told them this whole story, some of you have heard this before, about the chicken plant Anybody remember this story about the chicken plant? So, okay, so one of his professors was hired to help the chicken processing plant come up with a better way to process the chickens. Because if you've ever seen, like, I don't know how much you know about hunting or anything like that, but when an animal's slaughtered, you don't want it to thrash around because then it puts blood into the muscles and it's not good. You basically want all the blood to drain from the muscles. That's the idea, because that's the meat that you eat, right? You don't, like, if you cut a chicken's head off on a farm and it runs around headless, which they do sometimes, you kind of ruined it. That's why, like, an animal that's been hit on the side of the road, probably not good for eating, right? Even if you just hit it just now, because you don't want that blood to keep pumping through the tissue. You want it out. So what this man helped, so bizarre, helped them develop was a process to paralyze the chickens prior to removing their little chicken heads. So imagine the big pool with your electrolytes, your salt water in it, and you're running electricity through it. Now, Galvani realized that if you put muscles in contact with electricity, you can make them jump, but you can also make them freeze, right? So this man helped develop a system where they grab the little chickens by their feet, scoop them up upside down, dip their little heads in an electrified pool of salt water, which caused them to go, right? And like they jerked, they froze. And as soon as they emerged out on a conveyor belt, lines of chickens dangling headfirst into the pit. As soon as they come out of the pit, there's a little blade and walks them. It's terrible, but it's, if you like chicken, your chicken may have been processed in such a way, but all their little heads just dropped into a bin and their little bodies were frozen, like completely petrified as they came up, like Petrificus totalis, you know what I mean? Like, so yeah, it's very efficient. But he was charged, this professor was charged with helping come up with the method that had the right amount of electricity, because you don't want them to thrash, you just want them to paralyze. And how do you maintain that? And what level of electrolytes do you need? All of that. So that was part of what he learned. Crazy, but hey. So how do an acidic dry cell and an alkaline dry cell differ? Does anybody have this answer? Caitlin, what you got?
Potassium hydroxide.
There you go, exactly. So materials in dry cells are different. In an acidic dry cell, carbon rod and zinc case are used along with NH4CO. There's your nitric chloride there, which is acidic, and an alkaline dry cell, brass rod, and there's your potassium hydroxide right there. All right, so describe how a standard electrode potential is measured. Somebody that's not Caitlin. Oh, this is how we get binder credit. I'm now watching. Who doesn't have a coin? Describe how a standard electrode potential is measured. Oh, Colin? Yep.
Cells that is standard hydrogen electrode.
There you go. Connect a standard hydrogen electrode to a half cell in which the reaction of the interest happens using a salt bridge. The voltage of the electrode with respect to the standard hydrogen electrode is the standard electrode potential. Calculate. Who did this one? Calculate the voltage and identify the cathode for a cell in which the natural reaction between the following electrodes happens. Da-da-da. Drew, you got it? 0.76 volts. Yeah, there you go. All right, so very good. So yeah, there's your cell voltage. And then you use it. This was how you would calculate it. So a sacrificial anode is allowed to corrode. Why is use of a sacrificial anode considered to be a way to prevent corrosion? PJ.
Because the stuff of the metal that you want to protect.
There you go. So using this is terrible copy, but using a sacrificial anode is a way to prevent corrosion because the anode is connected to another metal, which is usually an important structural component. The metal is protected from oxidation, and the anode gives up electrons to the structural metal because the sacrificial metal oxidizes more easily. How does an electrolytic cell differ from a galvanic cell? Who's got that? All right, Drew.
The galvanic cell produces electrical. I can't remember. This electrical energy and.
Yeah. Galvanic cell generates an electric current spontaneously from a chemical reaction, and an electrolytic cell uses electrical energy to cause a reaction to happen. What chemical process occurs at the anode of an electrolytic cell? Jordan. There you go. Very good. We did that in lab. List 3 commercial products made by using electrolytic cells. Who got this? Bleach. All right, Caitlin, what do you have? Yeah, okay, yeah. So yeah, anything. Sodium metal, chlorine gas, aluminum, hydrogen gas, these are all things. Okay, somebody define electrolysis for me. What you got, Colin? That's one, yeah, yeah, you can do that. It's splitting by electricity. Water is one thing that can be done. Yes, splitting by electricity. Change is brought about by an electric current. So this reaction happens naturally. Explain why it's necessary to use an electric current to deposit a layer of zinc onto a copper bracelet. How do you get this one? So to deposit zinc on a bracelet, the zinc must be dissolved in a solution and the copper must be in solid form. So the reverse of the reaction shown is needed if the reaction happens naturally in the direction shown when the electric current is needed to cause the reverse reaction to happen. There you go. How do acidic and dry and alkaline cells differ? Didn't we just do that one?
Yeah.
I think we just did that one. Yeah, we did. Describe how standard electropotential. We did that one. Oh, somehow these got in here twice. These are the same ones. They got in here twice. Sorry, I don't know how that happened. All right. So you have an exam, a test, right? Unit 8. Here you go. These are your topics for Unit 8.
Not as bad as.
Yeah. This is a short unit because it's only 2 weeks. So it should all be, fresh in your mind. You shouldn't have to like struggle too hard to come up with anything. All right, gang. Next week, mystery lab. Bring your laptops, your tablets, your whatevers.
Yeah.
Bye. Goodbye, Kaden. Yes, I will. 1 second. Let me turn this off.